Hello everyone, myself Dr. A.Richard Praveendosss, Department of Mathematics, Assistant Professor, St.Joseph's College of Arts and Science, Autonomous, Cuddalore. Now I'd like to share something about the topic real analysis. I have chosen Unit 5, which comprises of open set and closed set. Before seeing open set and closed set, I like to say the definition of metric space. Metric space, for metric space, we are choosing X as a non-empty set, defining D from X cross S to R. Then D is said to be a metric on X if it satisfies the following condition. There are 4 conditions actually. First, non-negativity constraint. Non-negativity condition is nothing but distance between X and Y is always greater than or equal to 0 for all X, Y belongs to X. And definiteness, distance between X and Y equal to 0 if and only if X equal to Y. Symmetry relation, distance between X, Y equal to distance between Y, X. Triangle inequality, distance between X, Y is less than or equal to distance between X, Z plus distance between Z, Y, which holds for all X, Y, Z belongs to X. Some of the examples: metric space. We already seen the definition of metric space. A non-empty set along with the metric D is called a metric space, and it is denoted as X, D or simply X. Some of the examples: R is a metric space. We define some relation R cross R to R with relation distance between X, Y equal to modulus of X minus Y for all X, Y belongs to R. To check D is a metric on R, first it need to satisfy non-negativity restriction. Distance between X, Y equal to modulus of X minus Y, which is always greater than or equal to 0. Then definiteness, distance between X, Y equal to 0 if and only if modulus of X minus Y equal to 0, which implies X minus Y equal to 0 implies X equal to Y. Symmetry relation, distance between X, Y equal to modulus of X minus Y, which is equal to modulus of minus of Y minus X, which is equal to Y minus X, which equals distance between Y, X. Then triangle inequality, distance between X, Y equal to modulus of X minus Y, which equals to X minus Z plus Z minus Y, which equals to X minus Z minus Y minus Z. X minus Z plus Z minus Y, which is less than or equal to X minus Z plus Z minus Y, which equals distance between X, Z plus distance between Z, Y for all X, Y, Z belongs to R. Neighborhood of a point. Since D satisfies all the axioms of the metric, D is metric on R. It is called usual metric or standard metric. Now we are going to see neighborhood of a point. Definition for that neighborhood of a point is, we are choosing X be a metric, P a point belongs to X, then neighborhood of that point P is a set N of P over R, defined as N of P over R equals the set of all elements of X belongs to X such that distance between X, Y less than R. The number R is always greater than 0 is called radius of the neighborhood. Interior point. The definition of interior point: X be a metric, E is a proper subset of X. We choose a point P belongs to E, then P is said to be an interior point of E if there exists a neighborhood such that the neighborhood properly contained in E. Some of the examples: we take X a metric equal to R, E be a subset Z which is properly contained in R. Neighborhood of a point X is denoted as n of x over x, which equals x minus epsilon, open interval x minus epsilon, comma x plus epsilon. Now for finding, we take epsilon equal to 2, the neighborhood of minus 1 equals open interval minus 3 comma 1, which does not contain z. Now we cannot find any neighborhood of any integer which is contained in z. Therefore there is no interior point z. Open set. The definition of open set is, we take x be a metric and E is a subset of S. E is said to be open set if every point of E is an interior point. R is an open set. Example of open set is R. Then open interval minus 1 comma 5 is an example of open set. Then some of the examples: 0 comma 5 union 7, which is contained in R. We take some of the interior points as 0 and y. E is not open here. And if you take closed interval 1 comma 5, which is a proper subset of R, the point 1 comma 5 and all real between 1 and 5, interior point or real numbers between 1 and 5, which is not open. Theorem: every neighborhood is an open set. That is a proof of the theorem. We take x as a metric, p as a point in metric, then neighborhood of p we consider n of p over r. R is greater than 0. Now we need to prove n of p is an open set. For that, every point of neighborhood is an interior point. We need to prove that. We take q in the neighborhood. We have to prove q is an interior point. For that, distance between q, p and q equals h. We take h as a distance between p and q. Then n of q r minus h be a neighborhood of q. Now we need to prove n of q over r minus h is a subset of n of p over r. Now we take an element in n of q over r minus h. We need to prove x belongs to n of p over r. Now since x belongs to n of q over r minus h, the distance between x comma q is less than r minus h. Now distance between x comma p is less than or equal to x comma q plus distance between q comma p by triangle inequality. By using that, r minus h plus h equals to r. Distance between x comma p less than r, which implies x belongs to the neighborhood. Therefore there exists neighborhood, q is an interior point. From this we can say that it is an open set. Then derived set. A set of all limit point is called derived set of E, and it is denoted by E dash. Some of the examples are given. Then closed set. We take x as a metric, E is a subset of x, then E is said to be closed set if every limit point of E is a point of E. The example of closed set here, the example of closed set is 0 closed interval 0 comma 1. Thank you.